Welcome. In this session, we will learn how do we represent data in statistics, or how do we use different statistical measures or matrices to represent data, and how do we use these statistical measures to distinguish between different classes of data. In other words, the goal here is to learn different statistical measures or matrices that are used to model the data. Let's start. So the first statistical measure that we'll learn about is mean. So the first statistical measure that we have is mean. Now, mean simply tells us some kind of an average value of data. So mean simply defines some kind of an average of a given data. Let's take an example. Let's suppose our data is 1, 2, and 6. For calculations purposes, we'll take only 3 data points. So the mean or the average value of this will be, let's call that x bar. So the mean is defined simply as sum of the observations divided by total number of observations. Sum of the observation is 1 plus 2 plus 6, that's 9, divided by total number of observations, that's 3. So the mean value is 3. So this is how we calculate mean or average of this data. Similarly, let's take more examples to calculate this mean. Let's suppose we have 2 classes of data. Class 1, suppose the class 1 data is, let's suppose this is 4, 5, and 6. And class 2 data is, let's suppose this is 0, 5, and 10. So the mean or the average value of this class 1 will be, let's call it x1 bar. This will be simply 4 plus 5 plus 6 divided by 3, that's 4 plus 5 is 9 plus 6 is 15 divided by 3, that's 5. Similarly, the mean or average value of this class 2 is simply 0 plus 5 plus 10 divided by 3, total number of observations, that's again 15 divided by 3, that's 5. So the mean or the average value of both these classes is 5. Now, before we proceed, one simple trick to compute the mean or the average of the data is, if the data are given something like this, if the data is symmetrical across some point, as you can see, the data point 4 and 5 are at symmetrical. Symmetrical means they are at equal distance from this central point, that's 5. So the distance between this and this is 1, distance between this and this and 1. Now you don't need to calculate the mean value here, you can directly say the mean is simply 5. You can directly say the average or the mean is simply 5. So if the data points are symmetrical across a point, you can directly say the mean or the average value of this data is 5. Similarly, the second class, the data points are 0, 5, and 10. So the data points are 0, 5, and 10. And again, you can check these values, means 0 and 10 are again symmetrical across this data point 5, and these are at distance 5. Both are these at distance 5 from this. So you can directly say the mean value of this data set is simply 5. You don't need to compute this. So you can directly say these are 5. So this is how we compute the mean. This is how we calculate the mean of data. All right. The next question is mean always a good measure? Or does it model this data? Does this mean always give us a better picture, a representation of this data? Now, as you can see from this, no, and also you cannot use it to distinguish these 2 classes of data. As you can see, the data is completely different. However, the mean of both the classes is same, that's 5. And you can see the data points in this are at a distance of 1 and the data points in this class are at a distance of 5. So these are obviously two different classes of data. So how do we infer this information from this statistics? How do we capture this information? Means these are at a different distances from this mean or the center point. How do we get that information? For this, statistics has one more metric or measure to give us this behavior, and that's referred as variance. Now, before I discuss variance, let me tell you why mean is not always a good measure, or it does not give us the good picture of, always give us the good picture of this data. So suppose we have a student and we have students' grades in two courses. Suppose the courses are English and maths. And let's suppose the students score in maths, the students score 100 marks, and in maths, the students score only 0 marks. So what's the average marks of the student? So what are the percentage of student in these two classes? So you can say the average percentage or average marks of student is 0 plus 100 divided by 2, that's 50. Now, is this a good measure? This means the average marks of student in English and mathematics is 50. So the mean marks of the student is 50. So mean is not always a good measure to reflect this data set, to give us the information about this data. All right, so this is about mean. So it is not always a good measure of this statistical behavior. All right, so let's switch now to this variance. What do we mean by variance? Now remember, this variance simply tells us what is the measure, or simply what's the spread of this data. Spread of data around mean. Spread of the data that's given to us around this mean value. So that's what variance tells us. Now, how do we compute or how do we calculate this variance? What we do, we take the difference of each data point from this mean value and take the square of that distance, then take the sum of all these squares and divide by the total number of observations. This defines the variance of the data. To illustrate this, let me go back to the previous two sets. So my two data sets are 4, 5, and 6, and second data set is, sorry, let me try at a different distance. So another data set is 0, 5, and I know the mean value of both the classes is 5. Mean value is 5. So first I calculate the distance of each point from this mean value, and mean is 5, that you can check, mean is 5. So the distance between 4 and 5 is 1, distance between 4 and 5 and 6 is 1, and distance of this 5 from 5 is 0. All right. Similarly, the distance of this data point from mean value, that 5 is 5. Distance of this data point 10 from mean value is 5, and the distance of this 5 from itself is 0. So how do we calculate the variance? And variance is denoted by sigma square, and for class 1, let's call it sigma 1. So the variance here will be simply square of this distance, square of this distance, plus square of this distance. So it will be 1 square plus 0 square plus 1 square divided by 3. That is 1 square plus 0 square plus 1, and that's 2 by 3. Similarly, the variance of the second class of data is sigma square. Let's call it 2 sigma 2. So this will be 5 square plus 0 square plus 5 square divided by 3. That's 25 plus 0 plus 25 divided by 3 is 50 by 3. So this tells us that the variance, the spread of these two classes are totally different. As you can see, the spread of this data set 1 is 2 by 3 in class 1, and for class 2 the spread is 50 by 3. So and it's very obvious from these two data sets. The spread is more in second class as compared to the dot. That's how this spread is calculated, or this variance is calculated. Simply, we take the distance from the mean, then we compute the square, then we sum these square values divided by the total number of observations. That tell us what is the variance of these two classes of data. All right. So this is how we calculate this variance of the data, and this tells us what's the spread of this data across this mean value. All right. So before I proceed, if you want to use the formula for mean to calculate the mean is simply the sum of observations in summation xi, where I is running from 1 to n divided by the total number of observations which is n. And to calculate the variance, we say sigma square, and we compute first the, let me use this x1, then take the square of this distance, where I is running from 1 to n, then take the sum of all these distance square values, then divide by the total number of observations. Sometimes in this, instead of n, we use you will also see sometimes that this in variance formula you have, instead of n, use n minus 1. Let's not talk about that formula, why we use n minus 1 and where we use n. Let's skip that. Now, so this is how do we calculate mean and variance of the data. Now, if we have now two-dimensional data, means if the data is spread on a plane, how do we calculate variance of that data? That's the second question. So variance of 2D data. So variance of, that's our next topic. Variance of two-dimensional data. That's the next question. So that's our next question. Now suppose we have some data, and let me use small marker here. So I have some data. And this data, this is my data in two-dimensional space. And let's suppose this is y-axis and this is my x-axis. So this is my x-axis, this is my y-axis. Now, first, variance simply tells us what's the measure of spread. So first, what is the spread of this data across this axis? So what is the spread of this data in this direction? Similarly, what's the spread of the data in this direction? So spread of this data, how do we compute the spread of this data? Means what is the variation of this data in x direction? To calculate the spread in x direction, what we do simply, we neglect the height of this data in this direction. In other words, we neglect the variation in x direction. So we simply neglect variation in y direction. So to calculate the variation in x direction, we neglect the variation in y direction for time being. So what we do, we say this data is spread in x direction only. So this is, in other words, we project this data on x-axis, some kind of a projection of this data on x-axis, and we say this data is right here. So to calculate this variation or spread of this data in x direction, we project the data on this. I haven't mentioned the values of these data points that we shall discuss later. This is just the illustration. So this will give us sigma x square. So this tells us, this parameter tells us what is the spread in x direction, and we again use the same formula to calculate this. Means we do the same procedure. First compute the mean value, then take the difference of each data point from this mean value, take the square of that distance, sum these distance squares, then divide by the total number of observations will give us the variation in x direction. Similarly, to calculate the spread or variation of this data in y direction, what we do, we neglect the variation of this data in x direction. So we neglect x direction variation. Neglect x direction variation. What we do, what does it mean we neglected the variation in x direction? It simply means we project now this data on this axis. So this means some kind of a projection. When we neglect this, here the data points on y side are overcrowded, but the point that's important is that we say the data is, so to calculate the this variation in y direction, we neglected the variation in x direction and calculate this, and let's suppose the variation is sigma y square. So that's how we compare this, calculate the spread in x and y direction. To compare the, to calculate the spread in one direction, we neglected the variation other direction. That in other words means geometrically we're projecting this data on that axis. Similarly, to calculate the variation of this data in other direction, we neglect the variation in other direction and project this data on that axis, and that will give us the variation in that direction. So this is how we calculate variation in x and y direction. Now before we proceed, let's take an example. Let's suppose we have a data. Let's suppose we have some kind of a data, and the data looks like this. For calculations purpose, let me take only 3 data points. Let's suppose I have only 3 data points. Let's suppose the data points are these. This is my first data point, second, and third. Similarly, I have one more data set, and that data set is this. I have one more data set that looks like this. So these are my 2 data sets. Now let's suppose the coordinates. So this is a 2-dimensional data. This is a 2-dimensional data. So the coordinates of these data points are, let's suppose the coordinates of this are, for simplicity, let me take, to make the calculation easy, let's suppose the coordinates of this are 0, 0. Coordinates of this are -3 and 6. Similarly, coordinates of this are +3 and minus. Similarly, the coordinates here, let me suppose the coordinates here are, let's suppose these are -3, 6. To make the calculations easy, that's why I'm using these values. So this will be, and this should be -6. So these are my 2 data sets. So let me calculate the variation of these 2 data sets in x and y direction. First, as I can see, the mean value of these data sets are simply mean values in x and y direction are same. That's 0 in both the cases. That you can check using the similarity concept. You can get it directly. Now, what's the distance in x direction of this point from this mean value? So the mean in both the cases is same. Please check that mean the both in x and y direction is same. You can check that. So the mean value or the mean point of these data is 0, 0 in both x and y direction for both the data sets. Now, what is the difference of this mean point from this -3 and 6 data point? Now please have a look. So this is 3. So distance in x direction is 3. Similarly, what's the distance of this point from this mean value? Again, it's 3. Sorry, it's not 3, it's 6. Sorry, it's not 3, it's 6. Right, it's 6. So the distance is 6. So in this direction, the distance is 6. Similarly, I'm not drawing these points in scale. Please remember that. I'm not drawing these data points in scale. So please have a look at that. Now, similarly, the distance of these data points in y direction, means from the mean value in y direction, is mean in both x and y direction is 0, 0 of these data points. You can check that. See, this x value is 6, this value is minus 6, and the center of x value is 0. Sorry, I think I wrote it wrong. I think I wrote it wrong. So the distance here is not 6 but 3 in x direction, because first point represents x direction. Similarly, the distance here is 3. Now the distance in y direction is 6. You can check it is 6 from the mean value. Similarly, the distance here is 6. Please check it. Now let me repeat this procedure what I have done. See, the mean value in both the cases is 0. Why is the mean value 0? Let's answer that. Let's calculate first the x variation. See, x first data point in x direction is minus 3, second is at 0, third is at 3. I told you if the data points are symmetrical across a point, the central point is the mean. Similarly, if you go to the y coordinates now, it's at 6, 0, and minus 6. So again, in y direction, the mean value is y. So the mean value in both x and y direction is 0, 0. Same thing is true for the second data set, that's here, this here. So same thing is true for this data set. So now the distances from the mean value of these points. See, the mean value of this point, mean value of a point from itself is 0, 0. You don't need to mention it. So the distance of this point in the x direction is 3. Similarly, the distance of this point in x direction is 3. Now the distance of this point in y direction is 6. Distance of this point in y direction is 6. So distance from this to this is 6. And we know this point is the central point or the mean point of this. Same thing is true here. Let's go back here. Distance of this point from this point, means from the mean point, is 3. Distance of this point from the mean point is 3. So this is in x direction, now in y direction. So distance of this point from the mean value is 6. Distance of this point from the mean value is 6. So this is how we calculate the distances. Now the variation is in x and y directions. First for this data set, so let's call it sigma x, x1, means variance of data set 1 in x direction. Simply will be distance square, that is 3 square plus 0 square plus 3 square divided by 3. Total number of observations is 3. So what's this value equal to? 3 square is 9 plus 0 plus 9 divided by 3, that is 6. 18 divided by 3 is 6. Similarly, the variation of this data means of class 1 in y direction will be 6 square plus 0 square plus 6 square divided by 3, that's equal to 36 plus 36. So 36 plus 36 divided by 3. So this will be equal to 36. No, this is 24. So now let's go to the second data set. Now the variation in x direction, let's call it sigma xx2 square. So this will be again 3 square plus 0 square plus 3 square divided by total number of observations, that's equal to 3. That's so this is 9 plus 0 plus 9, 3. So this will be 6. So this will be 6 square plus 0 square plus 6 square. This is 36 plus 0 plus 36, and that's 24. That's 24. Now, as we can see, the variations of both the data sets are same. The variations of these data sets are same x and y direction. Although the two data sets are very different to each other. As you can see, the data sets are very different to each other. Now, let me redraw these data sets for distinction. So I have one data set that looks like this, and I have another data set that looks like this. And the coordinates of this are minus 3, 6, 0, 0, and this is 3, 6, minus 3, 6. No, this will be plus 3. Sorry, this is plus 3. The first data point is this is plus 3 minus 6. Similarly, the data set that's here, the coordinates are, what are the coordinates of this data set? Minus 3, 6, minus 6, 0, 0. This is 3. See, the two classes of data are totally different, but the variation is in x and y direction are same. So the next question is, how do we distinguish between these two data sets, which are totally different to each other, yet their variances, statistical variances, are both the same? So how do we set apart these two data sets? Now, can we have another statistical measure that can set apart these two data sets? That's the next question. So the variations in x and y direction for both the data sets, that's equal to 6, and the variations of these two data sets, y direction is 24. So the question is, although these two data sets look completely different to each other, yet their variances in x and y direction are same. Now, can we have another statistical measure that can set apart these two data sets? And the answer is yes. And that's referred as covariance. That is very, very important for us for future classes. That is very, very important. And that's referred as covariance. That's referred as covariance. So the covariance answers this question that these two classes are totally different. Let's see. So I have two classes of data. One class looks like this. Another class looks like this. So how do I set apart these two data sets? And the answer comes from covariance. Now, what's the concept of covariance? What covariance tells us? Covariance simply takes the product of the coordinate points. Means the concept of this covariance is take the product of these coordinates. Take the product of these coordinates of individual points. What do I mean by take the product of this? Let's redraw the data sets again. So I have two data sets, and the data sets are like this. This is my one data set, and this is my another data set. So this is my data set, and the coordinates of these 2 points, let me use a small marker for this. So the coordinates of this point 0, 0. Coordinates of this point are minus 3, 6. Coordinates of this point are minus 3, minus 6. Coordinates of this point are 3, minus 6. And the coordinates of this point are 3, 6. So these two are totally different data sets. You must remember these are two different data. This is my one data set. This is my another data set. And my aim is to distinguish between these two data sets. And the answer comes from covariance. And the concept behind the covariance is take the product of these coordinates. So let's first calculate the product of these coordinates. So what's the product of this? Minus 3 is 18, 0 plus 0 is 0, minus this is plus 18. So this is again plus 18. And the product of these coordinates is 3 minus 6. So this is the product. What we do in covariance, simply we take the product of coordinates, and sum the coordinates and sum that product divided by the total number of observations. That's what covariance is equal to. So the covariance of this data set and covariance of this data set. So how do I write it? Take the sum of these products. So for this data set, the sum will be equal to 18 plus 0 plus 18 plus 0 plus 18, and that divided by 3. So that's 1836. 36 divided by 3 is 12. So the covariance of this first data set is 12, and the covariance of second data set is minus 18 plus 0 minus 18. So first we take the product of coordinates of these data points, then we sum that product and divided by the total number of observations. This is minus. So covariance answers that the covariance of one data set is 12 and the covariance of other data set is minus 12. So the covariance of these two data sets, one is positive, another has negative covariance. So how do I tell these data sets apart? That covariance is this has positive covariance and this set has negative covariance. This set has negative covariance. And this concept is very similar to the correlation concept. This is very, very similar to the correlation concept. What's the difference between correlation and covariance? Correlation is standardized and the value varies from -1 to +1. Means correlation can be from -1 to +1. But covariance is not standardized, means it's not normalized value. It's not a normalized. So what this says, that data set 1 means this data set has negative correlation or simply negative covariance, means they are negatively correlated. Similarly, this data set is positively correlated or has positive correlation. And this is obvious. As you can see, as x increases here, y also increases. So as x goes up, y also increases. But here, you can check it. As x increases here, y decreases. That's the meaning of negative and positive correlation actually. So as x increases in this data set, so as x increases in this data set, y also increases. Now, the case is totally reversed here. As x increases here, y decreases. That's meant by negatively correlated. And this is very similar to in concept to the correlation. So that's how these two data sets are different from each other. Now, before we proceed, I want to consider one more data set and I want to calculate the correlation for that. I hope the concept of this covariance is clear. So how do we set these, again, let me repeat this, how do we set these two data sets apart? Covariance answers there are, this is a positively correlated data set, this is a negatively correlated data set. What is the meaning of negative and positive? I have those clear. If one coordinate increases, if the other coordinate increases, then it means they are positively correlated, or means they have a positive correlation or covariance. Similarly, if one coordinate increases and the other coordinate decreases, then it means they are negatively correlated, or simply if x increases, y decreases, means they will have negative covariance. Now, before we proceed, let me take one more example. Before we conclude this session, let me take one more. Suppose I have a data set and the data points are these. Suppose these are my data points. So these are my data points. Let me take a simple example. I am taking these values only for calculation purpose. I am taking the values here only for calculation purpose, so that calculations become very easy. That's the goal here, using these values. Otherwise, you can take any example. So this is 30. This is 3. This is 3 minus 3. So this is my data set, and I have 9 points in this data set. So what is the value of covariance for this? So the goal is to calculate covariance of this data set. All right, so what is the concept between covariance? Simply take the product of coordinates. So the product of coordinates is 9 here. Similarly, the value of this covariance is 0 here. It's plus 9 here. This 0 here. This is 0. So 0. This is 9. This is 0. This is minus 9. So what's the covariance equal to? So the covariance will be simply equal to, so covariance will be equal to minus 9 sum of all these products. Sum of all these products. Divided by 9. I have 9 data points. Plus 9 minus 9 plus 9 minus 1. So this is 0 by 9. That's 0. So this tells me the covariance between these points is 0. So the covariance is 0. And this is obvious from the data set. As x increases, nothing happens to y. Similarly, as y increases, nothing happens to x. They are neither positively correlated nor negatively correlated. That's why the covariance is 0 here. That's why the covariance is 0, means that they are neither positively correlated nor negatively correlated. That's why the covariance or correlation will be 0 for this data set. Okay, let's sum up this covariance concept now. Let's sum up this concept. First point, you must remember that to calculate covariance, what we do, we simply take product of these coordinates, product of coordinate points. Means the values of x and y data coordinate of these data points for this 2D data set. So that's the first point. Then what we do in second step, we take the sum of these product, sum of this product. And finally, we divide this sum by the total number of observations that gives us the covariance. That's the concept behind this covariance. Now, let me show you 3 data sets which are positively and negatively correlated. Let me use, so this is my x and y axis. So this is my xy coordinate system. So similarly, I have one more data set. And finally, I have a data set that looks like this. All right. Now, as you can see in the first data set, as this coordinate increases, the other decreases. So indirectly, they mean as x increases, y goes down, means these are negatively correlated, or they will have negative correlation, means the correlation between these two data sets is negative, or the covariance is negative. So this data set have negative covariance. Similarly, this data set is as x increases, nothing happens to y. Nothing happens to y, almost no variation in y direction. So we can say that this has zero correlation or very small correlation, or very small correlation, or very small correlation, or covariance. So that is the difference between covariance and correlation. Is one difference you can say that the correlation value is normalized. It varies from -1 to 1. Meaning is almost same. They have almost same meaning. So this data set, as x increases in this direction, y goes up. You can check it. So this will have, they are positively correlated. So here the data set is positively correlated, or this data set will have positive correlation. So this is how you can, just having a look at these data sets, you can say whether the data is having positive covariance or negative covariance or zero covariance, or whether the data sets is positively correlated, negatively correlated, or will have zero correlation. All right. Now remember, covariance is the fundamental concept in PCA. Now covariance is the fundamental concept in this PCA. Remember, covariance is fundamental concept in behind this PCA. What's it? What it does, means what's PCA, what it does, how it works, what's the principle behind, that we shall learn later. But this is the fundamental principle, means covariance is the fundamental concept behind this PCA. So we must learn it very well. So the concept of this variance, or in short, covariance, can be summarized by in 2D data set. For this 2D data set, we can summarize it by using a matrix that's called covariance matrix. That's called covariance matrix. Covariance matrix. So the concept of this covariance can be summarized by a matrix, means 2D data set. For a 2D data set, we can summarize it by a 2x2 matrix that's called a covariance matrix, and the elements of this 2x2 matrix are what is the variation in x direction and what is the variation of in y direction, and we write it at these elements are the covariance in x and y, the covariance in x and y. In terms of notation, you can also say it like this. This will be sigma xx square, means what's the variation in x direction. Okay, so what's the variation in y direction? Then we write here what's the this covariance between x and y. We write it sigma xy square and sigma y x or xy square, one and the same thing. All right. So this is how we write the covariance matrix. So this is the covariance matrix for 2D data set. And this point tells us what's the variation in x direction, what's the variation in y direction, and what's the variation, what is the dependence of x and y on each other. Similarly, what's the dependence of x and y on each other. So now we can extend this concept to 3D, 4D, 5D, and obtain the matrices. For example, the same matrix for 3D data. For 3D, means for 3-dimensional data set, covariance matrix will be simply this. Covariance matrix you can write as simply this. Covariance matrix for 3-dimensional data will be this. So the covariance will be what's the variation in x direction, what's the variation in y direction, what's the variation in z direction, and what's the dependence of x on y, what's the dependence of x on z? Similarly, what's the dependence of y on x or x on y? One and the same thing. Similarly, what's the dependence of y on z? Similarly, what's the dependence of z on x or x on z? Let me write this first. Let me write it here also, so that you remember what's the meaning of these terms. This is y. X. So do you remember this is the second row? So sigma 0 phi square. So what's the dependence of this? So this is the covariance matrix for three-dimensional data. So this is the covariance matrix for three-dimensional data. So this is how we get the variation of data in different coordinates in 1D, 2D, and 3D. And simply, if you have to calculate variance in x direction, what you do, if you have to calculate variance y direction, similarly in z direction, what you do, you say the data is not varying in the other directions and calculate the variation in that direction. But to calculate the covariance of any data set, what you do, you simply take the product of the coordinates and get the covariance. I hope the concept is clear. Now to further discuss this, let's switch to MATLAB and see how MATLAB calculates covariance of two vectors. Now MATLAB calculates covariance of the data. Let's switch to MATLAB. So let me share a different screen with you. All right, so this is our MATLAB. So let me take a very simple two-dimensional data set and let's see the covariance of these two data sets. 4 minus 7, 12, 9. So these are my two data sets. So what I'm going to do, first to calculate mean of any vector, you can say simply mean x. This will give you the mean value in this. So you can check the mean here is 13 divided by 3, that's 4.50. So mean is calculated right. Now to calculate this covariance, what I will do, I will see covariance x dash comma y dash. Now what does this dash mean? This will convert this row vector to a column vector. Dash converts this row vector to a column. And you can see this is a 2 by 2 array, as the data set is 2 by 2 because I converted these x and y into column vectors. So this is my two-dimensional data set, and this is the covariance matrix. So the variation in x direction is this, variation in y direction is this much, and this covariance of x and y is this. All right, this is how we compute the covariance. Now let me take one more example to show you what's meant by this 5, 3, 7. All right, so this is 1 minus 5, 7, 3, 4, 9, 8. So this is my array, and this is 3 by 4 array. Now if I type covariance of A, the answer will be a 4 by 4 array. Why? Because there are 4 columns in this A. Answer will be a 4 by 4 covariance matrix. Means this will take this column as one vector, this as another vector, this as another vector. This will assume this is a 4-dimensional data set. This is a 4-dimensional data set, and each vector I have 3 data points. So this will assume this is a 4-dimensional data set. So you can see the covariance matrix for this data set is 4 by 4. So the variation in x direction is this, variation in y direction is this, variation in z direction is this, variation in, you can say, u direction is this. And these are the dependencies of one variable on the another variable. All right. So these are very simple examples, but let me show you how do we represent this positive correlation, negatively correlated data, and this zero correlation data. For this, what I'm going to do, I'm going to generate data from MATLAB itself. Means I'm going to use MATLAB's inbuilt function to give me this data. So you can have the real life data also. Let me take, but this time what I'm going to do, I'm going to use MATLAB's inbuilt function to give me this this data, means which is positively correlated, negatively correlated, and that has zero correlation or zero covariance. And let me start with negatively correlated. And please don't worry about this. What is this mu sigma? These are just values of something. Don't worry about this. This will be clear later. This will be clear to you later on. So don't worry about this. What is this mu sigma? What I'm going to do to build this, to have this two-dimensional data that is negatively correlated, I'm going to use MATLAB's inbuilt function. I'm going to use MATLAB's inbuilt function. And what is this RNG and default inside? What is this? I will tell you the meaning in a minute. So what I'm going to do, I'm going to have a two-dimensional data set, and to generate this data set, I'm going to use MATLAB's inbuilt function. And this is the function, multi-valued Gaussian function. This is called multi-valued Gaussian density function. This is called the multi-valued Gaussian density function. All right, this is saying me the sigma matrix must be symmetrical. Let me use a different matrix. Let me suppose this is -1 and must be positive sigma. Sigma is this is 1 minus 2. Okay, so this will be -1 also. All right. So don't worry about this. What is the sigma? This will be positive sigma. What does it mean? Now what I am doing, this is the function that I was talking about. This gives me the two-dimensional data that is Gaussian, that has Gaussian distribution. Means this is the two-dimensional Gaussian distributed data, and I have 200 sample points. And what's the mean of that two-dimensional this density function? 2 and 2. So the mean value is 2 and 2. And variance, sorry, the covariance for that data set is 1, -2, -2, and 3. All right. So don't worry about this. What is this sigma, mu? This will learn later, but just this will give me the data. That's the whole idea. So I have now two-dimensional data in it. So you can, if you check the size of this, if you say whose x, you will see this has two-dimensional 200 rows and 2 columns in it. So each column has 200 data points in it. So how I'm going to refer it? For this, I'm going to use indexing out of the MATLAB. I hope that's clear to you, that I have already taught in the previous class. So to access the first column, so I will say all rows. This colon means all rows, but first column means plot x, and plot x. First column means give me the plot of first column of x versus second column of x versus second column of x. If I put colon here, means this includes all the rows, and to distinguish between rows and columns, we put a column, sorry, comma in between. So then what I'm going to do, I'm going to use a marker. And let's suppose I use plus this time. This is just a marker, don't worry about it. What's this plus? This means how the data points will be set on this graph. Means they will be denoted by plus. So if I enter this, you will have something like this. And to visualize this, let me share the screen with you. And this you can see, as x goes up, the other goes down. You can check as x goes up, the other goes down. You can check it very clearly. As x goes in this direction, y goes down like this. So this is negatively correlated. So let me switch back to MATLAB to give you, yes, this is negatively correlated. Let me check the covariance of this. Let me set to, so to get the covariance, I have to type X, first column, X, second column. See, you can check the covariance between this X and Y is minus. So they are negatively correlated, and the covariance in X direction is this, and the correlation or this covariance in X direction is this, and variation in Y direction is this, and these are negatively correlated. So this is a negatively correlated data set. Similarly, to have a zero correlated data set, what I'm going to do, I'm going to change the, here this is 0, this is 0, and I'm going to take it 1, and I'm going to again generate the data using, sorry, I should type, so this is my sigma, and use mu is 0, 0. Mean value of this two-dimensional data set will be 0, 0. Then what I'm doing R and G, and I'm setting the default value. See, what does this, what we say, MV N R and D. This is a multi-valued Gaussian distribution, and this time this is two-dimensional. Means multi-dimensional means you can have n dimensional, means 3-dimensional, 4-dimensional, 100-dimensional, 1000-dimensional this data. But what I am doing this time, I am having 2-dimensional, and this generates random data. But if you don't set this this RNG, it will change every time. So what I got, what result I got, you may not get the same. So what is this RNG doing here? What is this doing? This is simply setting the seed of that this function that's used to generate that pseudo-random data. So this is for reproducibility of this data, means to give you the same data. So this is only done to give you the same data what I have generated, so that you generate the same when you do this exercise. This is only for that purpose, otherwise you don't need it. And to generate that random data, what I'm doing, I'm using MATLAB's inbuilt function to do that, and that's multi-valued Gaussian density function. This time my data is two-dimensional. Sigma, then I'm having again 200 data points of this, and close it. Then what I'm going to do, I'm going to plot. First, let me have a different figure so that I don't close that one also. So you can check, let me share the screen with you. First figure window, the new figure window I generated. There is nothing on this figure. So to plot anything on this figure, what I'm going to do, I'm going to now do plot. This time my data is stored in Y, and I'm going, and this will be again stored in 2 columns. So each column has 200 data points. And what I'm going to do, I'm going to use a marker that looks like this, and the marker size I want equal to be, suppose 5. And let me label the x-axis. So this is x, and similarly y label. Now let me switch the plot to show you. So this has 0 correlation. This has 0 correlation. Nothing happens, as you can see. As x increases, nothing happens to y. The remains almost same. Means the variation in y direction remains almost, as x increases in this direction, y doesn't change much. Y doesn't change. So the correlation here will be very, very small. To prove this, let me switch back to MATLAB and check what is the covariance of these 2 columns of data. This is stored in Y. To access this, what I'm going to do, as you can see, the covariance between x and y is almost 0, means very small. So they have a very small correlation, almost equal to 0. Similarly, let me conclude with this session saying one more data set. And let's suppose this is okay. Let me use this value. Let's use the creation this. So let me set the seed first. To set the seed, we have to use RNG, and this sets simply the seed of this random function. Let me suppose this is all the z this time. So this tells me the error is because this should be a matrix, should be a positive semi-definite. And one, I hope this is okay now. All right, let me do an example of, let's suppose sigma is 3. It must be a positive semi-definite. And let's suppose that matrix is, this is my zero correlation matrix. Let me switch back to this. So let's suppose sigma is 1.5. All right, so this should be a positive semi-definite. What is meant by positive semi-definite, that we will learn in linear algebra most probably. All right, so this now Z has 2 columns with 200 data points in it. Let me plot this data. So instead of Y, the data is now in Z array, and that's 1 and 2. This time the markers I want to have are diamonds. So that D. And what I'm going to do, first let me clear this. I'm going to open a new window. That's figure 3. I'm going to open a new window. You can check. There is nothing on this window yet. So let me plot this now on this figure 3. Let me do that. So to plot it, so this will be in Z. But the marker I want to use is diamond sheet, and I want to label x-axis as X data. I want to label the y-axis as Y data. All right, so to show you this, let me switch the screen. All right, so you can check. This is a positively correlated data. As you can see, there are 200 data points in this set. So you can see as X increases, Y also increases. So this is a positive correlation or positive covariance. And to give you the proof, let me calculate the covariance. So instead of Y, the data is now Z. So this you can check, they are positively correlated. X and Y are positively correlated. All right, so this is my negatively correlated data set. As you can see, as X increases, Y gets down. So this is negatively correlated data. Similarly, I have zero correlated data, or a very small correlated, means the correlation is very small. You can check, you can use a different color for these markers, these data points. Similarly, I have a positively correlated data set. That's my figure 3, and you can see this is my positively correlated data. All right, so this is meant by variation. What do we mean by positive correlation, negative correlation, and zero correlation? I hope you understood the concept. So what was the aim of this lecture? How do we represent data in statistics? Means what are the matrices used to model the data? We just learned two. Means one was this mean, another was variance. Then we saw what's the problem of this mean and why we use it variance. Then we calculated the variance for two-dimensional data, and we saw to distinguish between different classes, there's different data sets. We use one more metric that's called covariance between data. And how do we calculate covariance matrix? We also learned that. Now to calculate this covariance in MATLAB, we also saw some functions there, and we type COV, simple. That means covariance. And I generated the data. To illustrate the examples, I generated the data by using MATLAB's inbuilt function that's called a multivariate Gaussian density function. And this function for that is MVN-RND. And the ingredients for this are the arguments of, it has two arguments. One is mu, another is sigma. What is mu, what's sigma, we will learn later on. And I hope this is clear to you. All right, let me stop here. In the next lesson, we'll learn linear transformations. What do we mean by linear transformations? All right.